Welcome to this third lecture in this lecture series on functional programming in F#. In the previous lectures, we talked a little bit about the reasons for learning functional programming and some philosophical reasons. It allows you to think about problems in a different manner, and it expands your brain. Today I'm going to talk about complexity, which is a far more pragmatic reason for learning and using functional programming. Tony Hoare said in his Turing lecture that there are two ways of constructing a software design. One is to make it so complicated that it has no obvious deficiencies. The other is to make it so simple that it obviously has no deficiencies, and that the latter is far, far harder. And today we'll have a little bit of a look on how functional programming can help with complexity. Before we start doing that, we should think a little bit about what these words mean. Some of this discussion today is stolen from Moseley and Marx Out of the Tar Pit, and some I have nicked from Rich Hickey, and you should go and watch his Simple Made Easy presentation for an in-depth, really great talk on how complexity affects our software. Something which is complex. Complex means intertwined, coupled, opaque. So that would be something that you would have spaghetti-like things that are knotted up like this. That would be very, very complex. Whereas something simple, from the word simplex, is something that is sort of straightforward, transparent, and it's easy to follow. And in today's world where we are writing software, we often find that the complexity grows very, very quickly. If we are writing a tiny little program, it doesn't matter what we do. We can keep it in our head, and the complexity is so small that there's no need to control it. We can write it in JavaScript, we can write it in Python, we can write it in assembler, whatever we like. But as soon as this problem starts growing, things start getting more and more difficult. And sooner or later, we will find ourselves having unintended interactions in our program, or bugs as we like to call them, where something interacts with something else at a distance, causing your program to malfunction. And if we think about this really, when we are writing programs, if we sort of do a little graph, and we have the timeline here, and we have what we could call speed of development on this axis. So if we think about it, what we usually find is that when we start writing on a new piece of a new software project, the first period of time, the speed is staggeringly fast. We start up here and it's going super fast. And we look at the thing and we say, oh, I'm going to be done in 2 weeks or a week. Next week I'll be ready with the whole project. And a week goes, and by the time we have added more code, our new development speed has dropped. So you say, oh, I'm going to be done in 2 weeks. So 2 weeks pass and we find ourselves here. And we say, oh, it's going to be 2 months. And after 2 months we are here. And as the number of lines of code grow, our speed of development goes slower and slower and slower, because we are pushing this heavy elephant through the room. But this is actually contrary to how it should be. Because when we start, we don't really have anything we start pretty much from scratch. So actually, we would expect things to go kind of slowly until we get sort of the infrastructure built so that we can start doing things quickly. So what we would like to see is something where we start at a fairly slow speed, and then as the time goes, instead, speed increases and then levels off at some fixed speed. Now, there's a discrepancy here. So both of these are, of course, idealized pictures of how the world would be. But the reason for the speed to dropping off with time is that complexity starts eating us. It's not just the complexity of causing bugs, it's complexity adding new things into this big framework that we have. How to make the pieces fit together. Everything is getting harder. Now, there are two types of complexity that we need to have in our mind, because it's sort of just to keep the picture clear. One is what we can call inherent complexity. That is built in the problem specification. As Rich Hickey said, it's not your fault. So, for example, quantum mechanics is hard. So if you're going to do a quantum mechanical program to solve some quantum mechanical problems, you are going to have to fight the complexity built into quantum mechanics. Now, quantum mechanics is expressed in mathematics, which again is a complex thing with its own complexities. If you could figure out a way of doing quantum mechanics simpler, then you would get a Nobel Prize, and it's not really sort of what we normally would do. So this is really the part of the problem specification. And if you have a customer and he wants a system to manage his warehouse and he has a complicated business, then the business rule here will be complicated. The spam filtering rules for Facebook's spam filter engine is like 200,000 lines, just the specifications, not the code. So things are complicated. That's this side. But then we have another, and this is not something we can do anything about really. So that's somebody else's fault. It's the world's fault. But then we have what we call incidental complexity. And this is complexity that arises from us trying to project the problem specification onto something. Having a computer is a complexity. Having an editor causes complexity. Having development tools causes complexity. Your programming language will introduce some complexity, and so on. And here we can do something, because we can choose how these things on this side of the graph or this table, how much complexity we will bring in with this. And that's important to remember. Another thing which is important to remember is that something which is simple is not the same as something easy. Easy is something we know, something we master. It's super easy if you're fit and you're young and you know how to do it, to do a standing backflip. If you're old and out of shape, it's very, very hard. But something which is simple is seldom easy, unfortunately. And Da Vinci said that simplicity is the ultimate sophistication. So people have been striving for simplicity in a long time, and it's usually very hard. Yes. So, complexity. We're going to look at complexity in software and see a little bit where does this complexity arise from. And if you read Moseley and Marx, they have a lot of different ideas on what's causing complexity. Personally, I think there is one feature of software which is causing the majority of complexity in our code. And that's mutable state. The moment we allow changing the value of something that we have already set the value to, we are causing enormous harm to our computer code. And I'll try to argue why this is. But just to have a little short example of how this actually works. I'm going to make it's a slightly contrived example, but bear with me. So let's try to program this following mathematical function, f of x, which is x plus 1 times x plus 2. And I'm going to make a Python implementation of this. And it's going to be a rather silly implementation. You wouldn't do it in the real world, but this is just to drive home a point. So def f of x, x equals x plus 1, y equals x plus 1, return x times y. So the first thing to note here is, usually when I give this example, somebody will say, hey, you have a bug there. Because it's x plus 1 times x plus 1, which is not what I was supposed to do. But then there's this little tiny trick here, because x comes in here, and note that there are no global variables. These are all local variables inside this so-called function, which is not really a function, as we will learn in this procedure. And the first thing I do is I increment x by 1, and then I increment it by 1 again, which is x plus 2, and then I return the result. And already here we can see that this is, just because I wrote it in a slightly silly way, this is actually forcing us to spend a fair amount of brain cycles on even trying to understand what this code is doing. And it's very easy to think that, oh, I made a mistake. And then you go in and add a 2. And then you made a mistake. So that's one thing. Now, another thing which is kind of interesting is that, what if I would flip these two lines? What would happen then? Well, actually, if I do, then I'm calculating a different function. Then I'm calculating x plus 1 times x plus 1, which is the same as x plus 1 squared. Because I have, in fact, introduced inadvertently, by allowing to change the value of x, I have introduced a time dependence. This is the imperative and then, and then, and then. So here we already see at this, in such a simple little example, by allowing x to change, how much trouble it's causing us. All right, so how would we implement this then? Well, if we just do def f of x, a equals x plus 1, b equals x plus 2, return a times b. Voila! Now in Python, if you would flip these two lines, it would be an error. Since, well, no, it wouldn't. That would work fine. I could actually write this as also as a plus 1, so that it mirrors that one perfectly. But now if I would flip the a and b, it would at least accept and stop functioning and say you have an error in your program. But if I write it as x plus 2, then it's easy to understand, and I can flip a and b as much as I like. There's no time dependence in it, and it just works. And the difference between these two definitions here is that this is a procedure. It's doing I/O, essentially. It's changing, writing to memory and changing memory there, whereas this one here is a mathematically well-behaved and defined function. Which means that in this case here, I can actually use mathematical reasoning about this function. It has mathematical properties. In this case, not really. It's not a function. Mathematics do not apply here. And remember again, we shouldn't be afraid of mathematics. Mathematics is something that is our friend, and it's just making sure that we are keeping things simple and boring and stable. One of the things that doing this actually destroys is a concept which comes from philosophy, which is called referential transparency. This is very important for being able to think and reason about things. Referential transparency means that we can replace a thing with its definition, an entity with its definition, straight. And if we look at this one here, anywhere where A occurs, I can just replace it with its definition. Anywhere where B occurs, I can just replace it with its definition. So I could just have skipped those two and just written it here. In this case here, I can't really. That won't work. So this one has broken referential transparency. This one is complex, this one is simple. One of the slightly nasty things with allowing variables and allowing I/O in arbitrary places is that any code that thing will touch will essentially lose its referential transparency property. Anything sort of, if this would call something below it here, if this gets called by something from above, this one gets called somewhere. The whole call stack is basically tainted. You cannot trust it. So if we think about a piece of code where we have here's the main, and that calls something, which calls something, which calls something, and we go down here, and then we call this function down here. This whole thing here is now tainted and is not trustworthy. And this tells us really that once we have learned about keeping things stable and nice, any type of I/O, any type of variable, any type of thing that we need to do needs to happen very close to the entry point of the program in call depth, localized. And then we should keep sort of the whole major basin of code should be kept pure. These are called pure functions. And I have no proof for this statement, but I conjecture that I think probably 70 to 80% of all bugs in live code come from some form of I/O or variable done in the wrong place. Now, if we forbid using variables, say that we don't have the possibility to declare variables, then suddenly we have maybe removed 70% of the bugs that we physically can write. The option isn't there. You just simply can't do it. You can try how hard you like, but it's not there. And that way we have already reduced the number of bugs in our program by maybe 60, 70, 80%. But this is just a conjecture, and it's based partly on just experience, what we see in our daily work. So if we say, okay, we can't, this is forbidden, and if we actually look at the statement like this, In a programming language, every line is a statement of truth, essentially. Every statement, every expression is a statement of truth. So what this is saying for the compiler, it comes down here, it looks at this statement, it says this is true, because it has a semantic meaning of updating a variable, so that's a valid thing to do in this case. That's a true statement. If it would be false, it would stop and throw an exception, say this is something wrong, you can't do this. Yes? So basically what we are saying is that x equals x plus 1 is true. But if you're a mathematician, obviously you would say that there's a line missing, which is that one, because x can never be equal to x plus 1. So there's a clue, although one is a formal statement and the other one is a semantic thing. But it gives us an idea that we're doing something nasty here that we maybe shouldn't be doing. Now, if we forbid this and say, well, x is never equal to x plus 1, then you pretty much automatically will find yourself ending up with functional programming in some form. Not quite, because there are other ways of doing things, but if you want to keep sort of a similar similar pattern of expression, then you will find yourself suddenly doing functional programming. And this is really one of the key features of why functional programming is important and why it's why we actually should maybe be doing more of it rather than imperative, because it reduces complexity. And later, when we're going to start looking at functions and using functions for abstraction, then we'll also find that that the functions themselves are incredibly powerful agents of abstraction. Once we have pure functions that we can trust, and we know that they are stable, we can start building complexity from simple components by composition. And then when we add type theory to the mix, and we get a language for expressing how functions fit together and how data fits together and how they compose, and then even add category theory on top of that mix, we get an extremely powerful composite for writing software, where we have very good guarantees that the code is correct. We sometimes joke that if it compiles, ship it when we're doing functional programming, because we in reality we see very few bugs, so we know from experience that this works. There are no guarantees though for that, but then very often it works really nicely. So that concludes the complexity part for today, and next time we'll talk a little bit more about abstraction, and then we'll start looking at functions, I think. Until next time.